talked about three of Newton's laws now. Yesterday, we talked about Newton's third law. Does anybody remember what Newton's third law said? I know Lane does because he gave me Newton's third law yesterday. But he gave it to me in a way that he learned it in junior high school, which is probably the way the rest of you learned it in junior high school, which is not my favorite way. I'm going to give me my definition, which I may be a little bit biased, but I think it's a little bit better. If object A applies a force on object B, then object B will apply an equal and opposite force on object A. If I kick the bedpost in the morning, the bedpost kicks me back. If I hit you in the face with my fist, which I would never do, by the way, then your fist is going to hit me back in the or your face is going to hit me back in the fist with an equal and opposite force. If I kick a soccer ball with my foot, then the soccer ball is going to kick me back in the foot with an equal and opposite force. If I throw a ball forward, I push on the ball forward, the ball is going to push back on my hand. Newton's third law, if object A applies a force on object B applies an equal and opposite force on object A. Now, can anybody tell me why I showed you the video with Wally and the fire extinguisher? Yeah, brother? Not exactly. You're on the right track. It is a Newton's third law thing, but you're not exactly right with the whole action-reaction thing there. Yep.
When you use the fire extinguisher, they would be pushing him, but Wally would also be pushing an exact pull back, so it would actually go.
Yeah, not exactly. Not exactly. Rucker, just raise your hand, okay? Not exactly. Not exactly. Rucker, do you have something to say? Yes, essentially yes. When he fires the fire extinguisher pushes on the powder coming out of the fire extinguisher, right? It has to, otherwise the powder's not going to go into the fire extinguisher. Newton's first law says the powder in that fire extinguisher will stay where it is. It's going to stay at rest forever until acted upon by an unbalanced force. So you push the powder out the back of the fire extinguisher. What does the powder do? If the fire extinguisher pushes on the powder, then the powder pushes back on the fire extinguisher. Wally's holding the fire extinguisher. So by Newton's third law, all he has to do is fire the fire extinguisher. The powder goes out. The fire extinguisher pushes on the powder pushes back. Wally and the fire extinguisher push backwards. Is that realistic? Absolutely it is. Yeah, that's a lot more realistic physics in that movie, at least in that part of that movie, than there is in a heck of a lot of other movies that are supposed to be more realistic than a cartoon. Okay, that works perfectly. It's very, very well done there. Okay? In the end, even when you saw Wally spinning around, what did he do when he was spinning around? Okay. Fired the fire extinguisher kind of off to the side to get a torque, right? To get him spinning around. You guys remember? It was last year, I think, about a year ago. A guy named Felix Baumgartner jumped from space, basically the edge of space, basically, and he actually broke the sound barrier as he came down, as he free fell towards Earth. He was going at something like 600 or 700 miles per hour, which is about 12 or 1300 kilometers per hour. He's traveling, just falling, free falling. And then when he gets into a more dense Earth's atmosphere, about 7,000 feet, he jumps, he opens his parachute, and then he glides to the ground, and it's all good. One of the big dangers for him was spinning. And he almost died, actually. He almost died, and it was a real risk. He knew that risk going into it. He said if he got spinning, what would happen? But if he got spinning kind of end over end, he's going to be a goner, right? Because what happens? If there's no air up there, and if he gets spinning, it's like a rotational inertia kind of thing, right? Instead of going in a straight line, you keep spinning forever and ever and ever. And that's kind of what was happening in the video there. As we applied this force kind of off center, and you start spinning, then he starts spinning faster and faster and faster, right? Okay. All that happens because Fire extinguisher pushes on the powder pushes back on the fire extinguisher. Does that make sense? For every action, there's an equal and opposite reaction. If object A applies a force on object B applies an equal and opposite force on object A. Who's a swimmer here? Anybody a swimmer like a competitive swimmer? Lots of people like to swim, right? You guys know how to swim, right? You jump in the water and you move your hands forward like this, and at least more or less like this. I don't have a very good swim form, but more or less like this. How do you go forward? How do you go forward in the water? You push on the water. So why do you go forward? Because you're not pushing on yourself. You're pushing on the water. What does the water do? The water pushes back on you with an equal and opposite force. So if I push on the force with 10 newtons, the water pushes back on me with 10 newtons. Yesterday we gave you an example of doesn't seem to fit with Newton's third law. We said we break the glass right here. We throw a rock at the window. Window breaks. Newton's third law doesn't apply, right? Because the force acting back on the rock isn't going to be the same as the force acting on the window. But it is. But it is the same force still. Okay, if the rock applies a force of 50 newtons on the window and it causes the window to break, well, then the window applied a force of 50 newtons back on the rock. Why didn't the rock break? Because the rock is stronger. Simple as that. The rock is stronger than the window. Why did the rock keep going? Let's not talk about energy here yet, okay? It's got inertia. So the rock wants to keep going. 50 newtons may be enough to slow down the rock, but it may not be enough to stop the rock. So the window applied an equal and opposite force backwards. It just wasn't enough to break the rock, and it wasn't enough to stop the rock. Sometimes it is. Sometimes it isn't. This concept of Newton's third law kind of makes sense to us? All right. Yesterday we took a look at some mathematics involving Newton's third law as well. For the most part, it involved the physics and the mathematics that we had done over the last few days with Newton's second law, finding forces acting on objects, multi-force problems. But we extended it to involve Newton's third law to analyze internal forces, the forces acting between objects. Remember we used the analogy or the example yesterday of the ice cream truck? Okay. We've got the boxes of ice cream or the blocks of ice cream inside the ice cream truck. There's the motion of the ice cream truck itself, but there's also the motion of the individual pallets of ice cream as well. Yesterday we were analyzing those individuals as opposed to the system itself. Let's take a look at the homework that we had last night. Page 136, number 1 to 4 and 8. We also had page 168, number 1 to 7. real quickly again, just because I realized I didn't have the sound turned on. My minimum force is going to be when I have my forces acting in opposite directions. My maximum force is going to be when my forces are acting in the same direction. What's the min force? 0 newtons, right? What's my max force? 200 newtons. Good? Let's take a look at our second set of questions now. We had 7 questions to work on here. Page 168, number 1 to 7. Any issues with any of those 7 questions? 1 to 7. Aiden? 4? 4, is that it? Any others? Going once? Going twice? Okay, number 4 it is. Number 4 says, state and sketch the action-reaction forces in each situation. Water pushes sideways with a force of 600 newtons on the centerboard of a sailboat. If water pushes sideways with a force of 600 newtons on the sailboat, what's the action force there? Yeah. The water acting on the sailboat. What's the reaction force? Go ahead. Sailboat acting on the water. I mean, how do you draw that? Well, here's the boat. Here's a force of 600 newtons acting on the boat. Here's the water. There's a force of 600 newtons acting on the water in the opposite direction. Same value, but opposite direction. B, an object hanging at the end of a spring exerts a force of 30 newtons down on the spring. What's the action force? The object pulling on the spring, right? That's the action force here. What's the reaction force? What happens as a result of it? What reacts to that force of the object pulling down on the spring? Why doesn't the spring fall? Why doesn't the object fall? Because the spring pulls back up on it, right? So I pull on the spring. What happens to me? Spring pulls on me. The object pulls on the spring pulls on the object. Does that make sense? If we wanted to draw that one, we could say, here's my spring. Here's the object. The object is, here, let's draw them separate, even though they're not. Okay, the object is pulling down on the spring. The spring is pulling up on the object with an equal and opposite force, both 30 newtons in that case. All right? Yep. Yep, absolutely. Number 5 says an object is resting on a level table. Are the normal force and the gravitational force acting on the object action-reaction forces? Explain your reasoning. That's a good question. That's a really good question. I'm glad you asked that one. Okay, here's the object on the table. We know that there is a force of gravity acting down on the object, right? And we know that the normal force will act up on the object, and it's going to be the same value because it's at rest, right? It has to be at rest. It has to be the same value. Otherwise, this object would either move downwards or it would move upwards. So it's got to be the same value. The only question now is it an action-reaction force? What's the answer to that question? What's the answer, Travis? Give me a yes or no answer. What's the answer to number 5? Are they both action-reaction forces? Okay, who says yes? Who says no? Okay, the answer is no. They're not. They're equal and opposite forces, but they're not action-reaction. Action-reaction forces, Newton's third law forces, act on different objects. Remember, if object A applies a force on object B applies an equal and opposite reaction force on object A. Both of these forces are acting on the same object, right? They're both acting on this. Therefore, they can't be action-reaction forces. Yeah. Okay. Maybe you got a table in here. Okay. So now we got a different problem here. Okay. If you're talking about the action-reaction forces, we're talking about the force of gravity acting on this object, and we're talking about the normal force acting on this object. Those are not action-reaction forces. Okay, now, if you talk about the force of the object pushing on the table and the force of the table pushing on the object, those are action-reaction forces, because that's two separate objects, right? The object pushes on the table pushes back on the object. But when we're talking about the force of gravity on the object and the normal force on the object, those aren't action and reaction. Yeah, Riker?
Considering that the Earth is the primary source of gravity, couldn't the Earth be considered an object?
Say that again?
Couldn't the Earth be considered an object?
Couldn't the Earth be considered an object? Sure it could. But that's not the question. The question is the force of gravity acting on this object. Okay, the force of gravity acting on this object. The normal force acting on this object. Sure, there's an action-reaction force between this object and the Earth. Sure. The Earth pulls on this object, the Earth pulls up on the Earth, or this object pulls back on the Earth. That's an action-reaction force, but it's not the question. The question is, the gravity force on this object and the normal force on this object, are they action-reaction? And they're not, because they're on the same object. To have action-reaction, they have to be acting on separate objects. The Earth pulls on the box pulls on the Earth. The box pushes on the table pushes back on the box. Okay? Action-reaction forces, two separate objects. Does that make sense? How many people got that one right? I know there was a handful of people that raised their hand when I said who votes no. They're not action-reaction forces, so it's good. I kick on the soccer ball kicks back on me. Is that an action-reaction force? Yes, because it's two separate objects, right? I kick on the soccer ball, object A pushes on B, soccer ball pushes back on me, object B pushes back on object A. Okay? I stand on the floor, force of gravity and the normal force on me. Are they action-reaction forces? No, because they're both acting on me. Now, if we talk about the force that I push on the floor with and the floor pushes back on me with, are those action-reaction forces? Yes, because we're dealing with two separate objects, right? The floor, and we're talking about me there. Two separate objects. Okay? I want to go back and do a couple more problems here today, just a couple, but they are a little bit trickier than what we did yesterday. Yesterday, we were asked to find internal forces, forces that act in between objects. So we talked about, say yesterday, 3 boxes. What's the force of object B acting on object C, or object C acting on object B? And we could do that. We learned yesterday that in order to do that, we had to analyze one particular object. We wanted to find the force of B acting on C. We had to analyze either object B or object C. And we're not going to change that. We're still going to do that. But yesterday, when we solved those problems, we were given the acceleration of the problem, of the question already. Today, we're not. We see this problem. We got a force of friction of 20 newtons acting on the 10-kilogram object. We have a normal force, a force of friction of 25 acting on the 15-kilogram object, and then we have an applied force of 50 newtons acting to the right on the system. We're asked to find the acceleration, and then we're asked to find the force of tension in the rope that joins the two together. Question B is not unlike what we did yesterday. But yesterday we were already given the acceleration. Today we're going to have to find it first. So let's do that. If we want to find the acceleration of the system, then we have to analyze the system. In the analogy that I gave you yesterday with the semi-truck, the ice cream semi-truck that my uncle used to drive, we talked yesterday about analyzing the individual boxes of ice cream in order to find forces that act in between them, the internal forces. But if we want to find the acceleration of the system, then we have to analyze the entire truck, including the ice cream. So let's pretend for question A, since we're trying to find the acceleration of the system, that this is a semi-truck, or this is a box, let's say, with 2 objects inside. It doesn't matter whether it's a 10 and a 15 inside, or a 20 and a 5, or a 25 and a nothing. When we're analyzing the system has a mass of 25 kilograms. So let's find the acceleration of the system by pretending it's one object. Let's draw a free body diagram for that one object that has a mass of 25 kilograms. We still have an applied force to the right at 50 newtons. We have a force of friction to the left of 20 newtons. And we have another force of friction to the left of 25 newtons. Now, those 2 forces of friction act individually on the objects within this box. First one acts, 20 newtons acts on the 10 kilogram object, the 25 acts on the 15 kilogram object. But if we're analyzing the system, we don't care about the individual effects. We care what effect it has on the system, the entire box. Now, technically, we also have this one and this one, right? Gravity and the normal force, but we know they cancel out. So, again, let's analyze the system here. Let's say F net is equal to the sum of the forces. Let's call this FF, FF1 and FF2. The net force is equal to the mass times the acceleration, since we're looking for A. Now we plug in our numbers. What mass do we use? Do we use 10, 15, or do we use 25? When we're analyzing the system, and that's what we got to do here because we're looking for the acceleration of the system. When we're analyzing the system, then we use the mass of the system. System weighs 25 kilograms. This box, or this semi-truck, has a mass of 25 kilograms. FF2 is neg 25. FF1 is neg 20. FA is 50. A becomes 0.20 meters per second squared. Is everybody clear on how I did that? We talked about what we did yesterday with Newton's third law, the idea of finding those internal forces, the forces that act in between objects. Okay, the force that acts in here. Okay, that's not what we're trying to do in question A. We're trying to find the acceleration of the system in question A. In fact, in question A, we're trying to do what we did last week. Get the acceleration of the system. It's just that last week, I wouldn't have told you that that system was made up of a 10 and a 15. I would have just said it's one object that has a mass of 25. But it's no different. Okay, this is exactly what we did last week. Get the acceleration of the system. Now, if we want to find an internal force, which this one is, the tension in the rope that joins the two objects together, the 10 and the 15, then what do we got to do now? This is what we did yesterday. Now we're not going to analyze the system. Now we're going to analyze one object. So pick one. Let's pick object number 2, the 15 kilogram object, and let's analyze it. It is a force to the right acting on it at 50 newtons. It has a force of friction acting to the left of 25 newtons. Is there a force of friction of 20 newtons acting on it? 20 newtons acts on the other object. Okay, if we're analyzing the system, then we have to count them both. But if we're analyzing one object only, then let's look at the force that acts on that object by itself, that object only. So 25 newtons does, in fact, act on the 15 kilogram object. Are there any other forces? Well, in order to keep the 10 kilogram object moving to the right, the 15 has to pull on it, right? If the 15 pulls on the 10, then the 10 must pull on the 15. Let's have another force drawn to the left. We'll call that the force of A on B. A's got to pull back on B. Now, how big is that? How long do we draw that arrow? We don't really know. We've just got to kind of guess and do our best with that. There is a normal force, and there is a force of gravity, but they cancel. Now we're going to say F net is equal to the sum of the forces. That's FF plus FAB plus FA. What mass do I use here now? 10, 15, or do I use 25? Hayden, which one do I use there? 10, 15, or 25? 15? Who agrees with that? Okay, who disagrees? Okay, those of you who agreed, good. I use 15. Why do I use 15 kilograms? Because I'm analyzing that object. If I'm analyzing the forces acting on the ice cream in the back of the truck, then I don't want to use the mass of the truck. Use the mass of whatever I'm analyzing the forces on, the box of ice cream, or the 15 kilogram object within this box. The acceleration we already know is 0.20 meters per second squared. It's the same value. If the truck accelerates at 0.2, then all of the boxes of ice cream inside the truck also accelerate at 0.2. We found the acceleration of the system. That will be the acceleration of both the 10 and the 15 kilogram object. FF is neg 25. FAB is what we're looking for here. FA is positive 50. 15 times 0.2 is 3. Equals 25 plus FAB. We're going to take the 25 over by subtracting, and we get FAB equals negative 22 newtons. So we've just found the force of tension in the rope that joins these two together. Had I chosen to analyze a 10 kilogram object in question B instead of the 15, what do you think I would have got for an answer? What do you think I would have got for an answer if I had drawn a free body diagram for the 10 kilogram object? Force of friction of 20 newtons backwards. We had a force of B acting on A forward. If I had to analyze that, what do you think FBA would have worked out to be? It would have been positive 22 newtons. Yeah, I could have analyzed that. In fact, because there's one less force acting, it probably would have been a little bit easier, right? It's going to be the same value, opposite direction. In a question like this, when we're simply asking for the tension on the rope, I don't care which one you do. And I don't care whether you get the negative or whether you get the positive, as long as you get the right number there, the magnitude correct. So what have we done there? Okay, this is what we did yesterday. We want to find an internal force, a force acting between objects, whether it's a rope or whether it's whatever, a force acting between objects, or just put it away and leave it away, okay? Then we analyze one of the objects. If we want to find the acceleration of the system, then we have to analyze the system. We look at everything external. The key words there, system. System goes with external. We want to see what effect there is on the entire system, and we got to go external and analyze the whole thing.